Hello everyone. Today I'm honored to present our work titled CasModaTest, a cascaded pipeline for self-directed model-agnostic unit test generation via large language models. This work is jointly conducted by researchers from Zhejiang University and the Douyin Community Limit. Our research aims to design an intelligent model-agnostic framework for automated unit test generation driven by large language models. Next, I will introduce the overall agenda of this presentation. This talk will proceed in 5 parts. First, I will discuss the research background and the limitations of existing methods. Second, I will explain the cascaded test framework. Third, I will present experimental results and analysis. Then I will highlight our key innovations and finally conclude with future directions. Now let us start with the research background. Existing LLM-based test generation tools face 3 key limitations. First, tools like Toga rely on pre-written test prefix, which restrict the developer's flexibility. Second, end-to-end generators such as Async test produce inconsistent test prefix and oracles, resulting in meaningless or invalid tests. Third, approaches like chat unit tests depend on proprietary models, limiting accessibility and posing data privacy concerns. This motivates us to develop a cascaded and open framework. CasModaTest adopts a cascaded pipeline composed of 2 primary phases, generation and verification. In the generation phase, the LLM first creates a test prefix that focuses purely on conducting test inputs, class initialization, and method calls. Then, a second prompt guides the model to generate the test oracle, specifying expected outputs and exceptions. In the verification phase, the generated prefix and oracle are automatically assembled into a component JUnit test case. The system performs compilation, execution, and self-repair if failures occur. This cascaded design divides responsibility between stages. Generation ensures diversity and coherency, while verification enforces correctness and stability. Together, these phases create a self-directed model-agnostic workflow for reliable unit test generation. Next, I will introduce how structured demonstration pools guided the generation process. To improve LLM guidance, CasModaTest introduces structured demonstration pools, which serve as curated repositories of human-written examples. The prefix pool contains demonstrations describing how developers typically construct class instances, initialize parameters, and call methods. The oracle pool focuses on examples of valid assertions or exception expectations, covering different assertion types like equality, null checks, and throwing exceptions. By splitting examples into these 2 pools, the model learns context-specific generation strategies instead of producing entire tests at once. This approach provides the LLM with explicit context boundaries, allowing it to generate semantically coherent and logically linked components. As a result, the generated tests better reflect developers' intent and real-world coding style, Next, I will discuss the prompt design that connects these demonstration ports with LLM. CasModaTest employs a dual prompt mechanism to ensure precision guidance of LLMs. The prefix prompt explicitly instructs the model to generate only the test setup and input data without writing any assertions. This keeps the prefix generation phase focused and prevents premature oracle generation. Then, the oracle prompt uses the partially componented tests as context and directs the model to replace oracle placeholder with a semantically matched oracle. This structured prompt ensures that each oracle logically corresponds to the prefix, avoiding mismatch expectations. Moreover, the prompts are templated to include project-specific metadata such as class name, method signature, and return type. This level of control minimizes hallucination and ensures reproducibility across projects. Next, I will describe how CasModaTest validates and repairs the generated tests. The verification phase of CasModaTest ensures that every generated test is both syntactically and semantically valid. First, the prefix and oracle are assembled into a JUnit test sketch with necessary imports. The system then performs a compilation check. If any syntax errors occur, CasModaTest automatically invokes the LLM to repair them via targeted feedback prompts. After successful compilation, the execute check validates runtime behavior. If an exception or logical failure arises, the framework triggers another repair loop. Each test can undergo up to 3 compilation and 2 execution repair iterations, ensuring high reliability while maintaining efficiency. We evaluate CasModaTest on the DefectForger benchmark, covering 5 Java projects: CLI, CSV, JSON, chart, and LLM. Additionally, we include Balance, a project unseen by GPT 3.5, to assess generalization. Baseline include CasModaTest, A3 test, Chat unit test, CloudLM, and EvoSuite. Metrics cover accuracy, focal coverage, and code coverage at multiple levels. Next, I will present our experimental results. CasModaTest achieves an average accuracy of 77.16%, overperforming all baselines compared with the CloudLM's 48.04%. Our framework shows a significant 29% improvement. This demonstrates that cascaded generation enhances both precision and consistency of tests. Next, I will focus on focal method coverage. CasModaTest reaches 81.93% focal method coverage, surpassing Chat unit testers 79.68%. On the LLM project, it achieves 88.49%, 5 above CloudLM's 70.06%. These results show that CasModaTest can focus on core functionalities with fewer model calls. Next, I will present the comparison with EvoSuite. CasModaTest surpasses EvoSuite by 20.3% in method coverage, 3.94% in line coverage and 4.8% in branch coverage. This improvement shows that LLM-guided test generation can outperform search-based algorithms in coverage and quality. Next, I will discuss performance on unseen datasets. Unbalanced dataset unseen by GPT 3.5, CasModaTest achieves 89.87% method coverage, while Evosuit fails to generate tests. This demonstrates strong generalization and robustness across unfamiliar projects. It confirms that CasModaTest is not overfitted to benchmark datasets. CasModaTest supports both closed-source LLMs like GPT 3.5 or 4 and open-source ones like CodeLlama and DeepSeek Coder. It achieves 85.75% accuracy with GPT-4 and remains competitive even with open models. This flexibility ensures both accessibility and data privacy. First, CasModaTest introduced Cascaded generation, which suppresses prefix and oracle creation. This design ensures semantically consistency and addresses the unpaired component issue in prior tools. By decoupling the stages, we achieve fine-grained control and better repairability. Next, I will discuss further innovations. Second, structured demonstration pools enhance in context learning. Third, CasModaTest achieves true model agnosticism, supporting both open and closed LLMs. Together, these innovations enable higher accuracy, scalability, and real-world capability. Next, I will conclude this talk. CasModaTest effectively overcomes key limitations in LLM-based test generation, including incomplete inputs, semantic mismatch, and closed-source dependence. It achieves the state-of-the-art accuracy and coverage while maintaining model flexibility. Overall, CasModaTest provides a reliable, extensible, and self-directed pipeline for test automation. Next, I will outline further directions. In the future work, we plan to extend CasModaTest to multi-language test generation beyond Java. We also aim to integrate static analysis for handling complex methods and improve self-debugging or for runtime errors. These enhancements will further strengthen CasModaTest's practicality in industry scenarios. Next is the final Q&A slide. This concludes my presentation. Thank you for your attention, and I welcome any questions or discussions.